Good afternoon, all of you. I am Dr. Siddhartha Samanta, Assistant Professor of Haldia Institute of Technology. Today I discuss about very important topic in your organic chemistry, that is organic spectroscopy. Now, what is spectroscopy and why we study this spectroscopy? Actually, spectroscopy is a branch of physical chemistry which deals with the interaction of electromagnetic radiation and the matter. So basically organic sample that containing multiple bond, that containing some functional group. By the spectroscopic technique is we understand which type of functional group are present. Suppose you synthesize one new compound in your lab, in your research lab, in your chemistry lab, but you do not know what type of functional group are present in the molecule. So you use spectroscopy technique and you identify what type of functional group are present. In your syllabus there is four several spectroscopy techniques are present. One is UV visible spectroscopy. One is UV visible spectroscopy. Another is IR spectroscopy. Another is NMR spectroscopy. And another is mass spectroscopy. So there's four type of spectroscopy techniques which are present. Today I discuss about UV visual spectroscopy. Okay. Now what is UV visual spectroscopy? A UV visual spectroscopy is a type of absorption spectroscopy in which light of the UV region, that is 200 to 800 nanometer region. This 200 to 800 nanometer region electromagnetic radiation absorbed by a molecule and electronic transition takes place. That is bonding molecular orbital to anti-bonding molecular orbital. This type of electronic transition takes place. There is a simple schematic diagram of UV visual spectrometer. In this UV visual spectrometer, there is a light source are present. There is a monochromator, and in that there is you take sample solution in the cuvette. You take sample solution, and this is the detector. So when UV light, this is light source is UV light, UV visible light, and the wavelength of the light is 200 to 800 nanometer. When it passes through the solution absorbs some energy, and when it's absorb energy, some electronic transition take place from bonding to anti-bonding. That is HOMO to LUMO transition take place. And this is the UV visual spectroscopy, and from detector you calculate the graph, you identify the data, and from this data you correlate with graph. Now, what is the principle of UV visual spectroscopy? UV visual spectroscopy is based on Lambert's-Beer's law. So according to Lambert's-Beer's law, absorbance of intensity light absorbance is proportional to absorbance A is proportional to concentration of the solution, and it's also proportional to path length, that is L. So absorbance A is equal to epsilon C into L. That is, this absorbance is equal to epsilon CL. What is epsilon is the molar absorptivity, and C is the concentration of the solution, L is the path length. And this absorbance is equal to log I0 by I. What is I0? If the intensity of incident radiation is I0, and after absorbing light absorption, so intensity of transmitted light is I, then absorbance is equal to log I0 by I, and this log I0 by I is equal to epsilon CL. So absorbance is equal to log I0 by I is equal to epsilon C into L. So this is the Lambert's-Beer's law. So from this theory, from this equation, you also calculate the concentration of unknown solution also. Now what type of electronic transition take place in UV visual spectroscopy? Basically organic molecule that containing lone pair, that containing double bond. If we take acetone, that is CH3 CO CH3. So in acetone molecule they are containing sigma bond, pi bond, and oxygen also containing lone pair. There is lone pair also present. So in that case, number of transition take place. So it's sigma to sigma star transition take place, n to sigma star transition take place, pi to pi star transition, and n to pi star transition take place. Higher energy is required for sigma sigma star transition and for n to sigma star transition. So it is require higher energy, and it is they are basically not observed in UV visible region. And in case of n to pi star transition and pi to pi star transition, that is most common transition observed in organic molecules, and it's require less energy. This type of energy, less energy is required for n to pi star transition. So energy order is sigma to sigma star transition require more energy, then n to sigma star transition, then pi to pi star transition, and then n to pi star transition. So lowest energy transition is n to pi star transition, and highest energy transition is sigma to sigma star transition. So we know that this energy is proportional to, inversely proportional to wavelength, that is lambda. So it's require higher energy, that is lower wavelength, and wavelength of light is less than 150 nanometer. Whereas n to pi star transition require lower energy, but wavelength of the radiation is in between to 200 to 600 nanometer. That is in the UV visible region. So this is the type of different transition. Now we discuss different definition in UV spectroscopy. One is chromophore. What is chromophore? Basically, chromophore is a color producing group. That is unsaturated functional group that are present with a molecule that are absorbance is shifted towards lower wavelength region. And this type of functional group are known as chromophoric group. So basically they are unsaturated functional group like alkene, alkyne, nitro, cyano. This type of functional group are known as chromophoric group. For ethene, that content only is carbon-carbon double bond. This type of chromophore, actually what type of transition take place? Pi-pi star transition take. But in case of carbonyl, CO molecule, NO molecule, in that case pi-pi star transition take place as well as N to pi star transition take place. So carbonyl molecule, NO molecule, in that case N to pi star transition and pi to pi star transition. So this is the chromophore. Now we discuss about oxochrome. Oxochrome is a saturated functional group that does not absorb energy less than 200 nanometer, but when it is present with chromophoric group, the color intensity of chromophore is increases. So this type of functional group are known as oxochrome, like OH functional group, SH functional group, NH2 functional group, NHR functional group. So this type of functional group is known as oxochrome. Like an example, benzene itself absorbs energy 255 nanometer. But when OH functional group attached with benzene ring, its absorption shifted to 270 nanometer. That is absorption energy also shifted to longer wavelength region. So this type of functional group is known as oxochrome. Now, what is bathochromic shift or red shift? This shift of absorption went to longer wavelength region. That is when some oxochrome or chromophoric group are present with the molecule, the absorbance shifted towards longer wavelength region. And this type of shift is known as red shift or bathochromic shift. Now, if we consider benzene, its absorbed energy 254 nanometer. That is, this is the lambda wavelength and this is absorbance. So in case of benzene, the absorbance like this, and this absorbance maximum is 254 nanometer. This is 254 nanometer. But in presence of NH2 functional groups, that is shifted towards longer wavelength region. Like that, in presence of NH2, it is somehow shifted longer wavelength region. That is, its absorbed energy 280 nanometer. 280 nanometer. So this is shifted towards longer wavelength region. This is known as bathychromic shift. Why this type of shift is observed? In presence of oxochrome, changing solvent polarity, increasing conjugation. So here you see that NH2 also present lone pair, and this lone pair is conjugated with the benzene ring. Due to this conjugation, wavelength energy absorbance is shifted towards longer wavelength region. So this effect is known as bathychromic shift or red shift. Now hypsochromic effect or blue effect or blue shift. This shift of absorbance band to shorter wavelength region. So here some phenomena, some functional groups that are reduce or remove the conjugation, this is shifted towards shorter wavelength region. Like NH2 aniline, absorbance is 280 nanometer, but in acidic medium, it is shifted towards shorter wavelength. Anilinium ion, its absorbed energy 203 nanometer. Why it is absorbed, this energy is less than aniline? Now this is due to this lone pair are not available for conjugation with the benzene ring. In case of aniline, this lone pair is available for conjugation. But in case of anilinium ion, in that case, this lone pair are not available for conjugation. So here blue shift is observed. Like that, shifting towards shorter wavelength region. So this is known as hypsochromic shift or blue shift. Now, what is hyperchromic effect and what is hypochromic effect? It is defined as an effect due to which there is increase in absorption intensity. So in that case, absorption intensity is increases. Okay, absorption intensity is increases. This type of effect is known as hyperchromic effect. For example, pyridine absorbs energy at 257 nanometer, and epsilon max is 2750. But in case of 2-methylpyridine, its absorbance maximum is 262 nanometer and epsilon max is 3560 nanometer. So initially, if we plot this, this is the shifting. Wavelength and epsilon. So epsilon max increases in case of 2-methylpyridine, and this is known as hyperchromic effect. And in case of hypochromic effect, this intensity is reduced. Intensity of absorbance is reduced. So what is the example in case of biphenyl system? Biphenyl. So biphenyl absorbs energy 250 nanometer and epsilon max is 19,000. Biphenyl system. This is biphenyl ring, two biphenyl ring. They are planar in geometry. They are planar, same plane. They are remain in same plane. So they are conjugated with each other. So it absorbs energy 250 nanometer and epsilon max is 19,000. But 2-methylpyridine if one methyl group is present, due to methyl hydrogen interaction, this methyl hydrogen interaction, the planarity is lost. Due to this type of repulsion, the planarity of 2-biphenyl ring is lost. And for this reason, due to loss of planarity, its absorbance intensity also reduced. So this type of effect is known as hypochromic effect. Hypochromic effect. Now, if we know the structure of the molecule, then we usually find out the lambda max value by using Woodward and Fisher rules. Two scientists, Woodward and Fisher, they formulated a rule. If you remember some data, if you remember some value, you easily calculated the wavelength of absorbance of compound. So if you know the structure, if you know the some data, you easily calculated the lambda max value. So you remember for homoannular diene system, the base value is 253 nanometer. For acyclic, base value is 217 nanometer. For heteroannular diene system, base value is 240 nanometer. For extended conjugation, this value is plus 30, you add plus 30. For exocyclic double bond, you add plus 5. For one exocyclic double bond, you add plus 5. For alkyl group, for R group, you add plus 5. For OSI 0. For S alkyl group, plus 30. For O alkyl group, plus 6. For NR2, plus 60. For chloro-bromo substitution, plus 5. So you remember this value. So from this value, we easily calculated the lambda max value of unknown compound. Now, what is homoannular diene system? Suppose you consider this system. You consider this system. So when two double bond present in a same ring, so this is known as homoannular system. But in case of heteroannular system, two double bond are present at different ring. Okay, different ring. Like that way. That is heteroannular system. Or maybe you so this is heteroannular system. So when two double bond present in a same ring, this is known as a homoannular system. When two double bond present at different ring, ring A and ring B, different ring, so this is known as heteroannular diene system. For acyclic system, if there is no cycle, this type of system is known as acyclic system. And for exocyclic double bond that are present outside the ring, this type of double bond is known as exocyclic double bond. For one exocyclic double bond, you add plus 5. For alkyl group, you add plus 5. Now, here you calculate some example of calculation of lambda max value. As in that case, this is acyclic diene system. Okay, this is acyclic diene. So for acyclic diene, you add 217. This is the base value of acyclic diene. And in that case, you see that there is two substitution are present. Ring residue for two alkyl group at 10. Okay. And this double bond is known as exocyclic double bond. For exocyclic double bond, you add plus 5. So total 232 nanometer is 232 nanometer. And observed value is 237. Okay. In that case, this is heteroannular diene system and base value here we consider 240. This is the base value. So here you see that this is your system. And This is R group, alkyl group. So here 3 alkyl group are present or 3 ring residue are present. For 3 ring residue, add 3 into 5, that is 15. 3 is ring residue 5, so 3 into 5, that is 15. And this double bond is exocyclic double bond. If we consider that is A ring and another is B ring, okay, for A ring, this double bond is called exocyclic double bond. For one exocyclic double bond, we add 5 plus 5. Okay, these double bond are not a exocyclic double bond. This double bond is exocyclic double bond. So total is 234 nanometer and observed value is 235 nanometer. So in that case, here you see that this system is homoannular diene system and this system is heteroannular diene system. So in such case, we take the homoannular diene system and base value is 253. Okay, base value is 253. Now, okay, now in that case, what is the, this is the system. Okay, so here alkyl group 1, 2, 3, 4 and 5. Okay, so 5 alkyl group are present, 5 ring residue are present. For 5 ring residue, 5 into 5, that is 25. And 3 exocyclic bond, that is, if we consider that is A ring, B ring and C ring. Okay, for A ring, this double bond is exocyclic. For B ring, this double bond is exocyclic, and for C ring, this double bond is exocyclic. So 3 exocyclic double bond are present, and we add 15. Now, if we consider this is homoannular diene system, then this double bond is extended conjugation. For extended conjugation, you add plus 30, and total value is 323. Okay, so this is the calculation of unknown compound, unknown sample by using Woodward and Fisher rule. Now we also identify isomer. If we taken this type of compound, we easily identify by using UV visual spectroscopy. This is the heteroannular diene system. This is the homoannular diene system. For homoannular diene system, lambda max value is more, and for heteroannular diene system, lambda max value is less. So by using UV visual spectroscopy, we also identify which one isomer is homoannular system, which one is heteroannular system. Okay. Now, extent of conjugation. So, we also identify which one is conjugated system, which one is non-conjugated system by using UV visible spectroscopy. Generally, as a conjugated system, conjugation increases lambda max value. Lambda max value also increases. So here we see the data. This is non-conjugated system. This is conjugated system, 1,3-butadiene system, and this is hexatriene system. So if we increase the conjugation, then lambda max value also increases. You know that from MO energy theorem, molecular orbital theorem, the pi molecular orbital of ethylene molecule, in that ethylene molecule only 2 MO is observed. One is bonding, another is antibonding, that is psi 1 and psi 2 star. Okay. This is the energy gap between HOMO and LOMO for ethylene. But in case of butadiene system, this is butadiene system, the energy, 4 energy is observed, psi 1, psi 2, psi 3 star and psi 4 star. So energy gap is reduced, that is psi 1, that is psi 2, that is psi 3 star and that is psi 4 star. So 2 electron. Now in that case, this is HOMO, and HOMO to LUMO transition, that amount energy is required. So conjugated system reduce the energy gap between HOMO and LUMO. So HOMO and LUMO energy gap is reduced. So if we add some energy, it is easily shifted from HOMO to LUMO. So easily electronic transition take place in that case. So conjugated system increase the lambda max value. And generally non-conjugated compound have absorbed energy due to pi transition less than 200 nanometer, whereas conjugated system is greater than 200 nanometer. For this system 219 nanometer absorbance, and this is 269 nanometer. So absorbance also increases in that case. Now here are some example. In case of naphthalene, this is the UV-VIS spectrum. Anthracene, this is the UV-VIS spectrum, and tetracene molecule. So in that case, more conjugated system, so effect of conjugation on absorption spectroscopy shifted towards longer wavelength region. So in that case, rate shift is observed basically. Now steric effect. Steric effect compound, we basically identify which one is cis isomer, which one is trans isomer. So sister isomer also separated by UV-VIS spectroscopy. In case of trans isomer, trans stilbene, this is trans stilbene for more conjugated system. But in case of cis isomer, due to steric repulsion, steric hindrance, planarity is lost, and it's absorbed 280 nanometer, whereas trans isomer it absorbed 296 nanometer. So cis-trans isomer we also distinguish between cis-trans isomer. Now what is the solvent effect? Which solvent is suitable for UV-VIS spectroscopy? A more suitable solvent is one which does not itself absorb in the region under investigation. A dilute solution is suitable for UV-VIS spectroscopy. Now we maybe use ethanol, methanol, water as a solvent for UV-VIS spectroscopy. But in case of benzene, its absorbed energy 280 nanometer. If we study organic compound like acetone, acetone absorb energy 279 nanometer. It is near about 280 nanometer. For in that purpose, we do not use benzene as a suitable solvent. Why? This is already absorb energy in the same region. Okay. So the absorption maximum for non-polar compound is same in alcohol as well as hexane. So there is no bar of solvent polarity. Okay. But for polar compound, alpha beta unsaturated carbonyl compound, it is affected by solvent polarity. Now solvent effect of alpha beta unsaturated carbonyl compound. So in case of alpha beta unsaturated carbonyl compound like that, what type of electronic transition take place? In that case, maybe N to pi star transition take place, and pi to pi star transition take place. So what is the effect of solvent in that case? So in case of N to pi star transition, in such case the absorption band moves towards shorter wavelength. Why it is shifted towards shorter wavelength? You see that in N to pi star transition, this is non-bonding, this is pi star transition, non-polar solvent. If we increase polarity N to pi star, if we increase polarity, what effect? Increased polarity, non-bonding is more stable due to hydrogen bonding interaction. In solvent, polar solvent, it is more stable and its energy is lower energy in polar solvent compared to pi star. So pi star like that. So initially you require this energy, and this is the energy gap. So N to pi star transition shifted towards shorter wavelength region. So for example, if we consider acetone, It's absorbed 279 nanometer. In acetone 279, in hexane water 264. For example, absorption maximum of acetone 279 nanometer in hexane. So hexane is a non-polar solvent, but in case of polar solvent, it is shifted towards shorter wavelength region, 264 nanometer. Okay. So solvent polarity affected in alpha beta unsaturated carbonyl compound, but pi to pi star transition shifted towards longer wavelength region. Okay. So what is the application of UV-VIS spectroscopy? Distinct in conjugated and non-conjugated system, we separate which one conjugated, which one non-conjugated system. Determination of configuration of geometrical isomer. It is used to determination of impurities present in the sample, and also we determine the unknown concentration of the solution can be determined. Okay.